All right, continuing where we left off last time, 0.02, in other words, 0.2 operations on polynomials. So this picks up right where we left off last time. Notice it's the same problem. You should have this one filled out. And we're going to take the idea from last time, our exponent rules, and we're going to start using them to perform operations on polynomials. Now, no, we're not going to be doing brain surgery. Operations means things like addition, subtraction, and today we'll touch on multiplication. We won't quite get to division yet, but we're going to focus on those three today. However, before we can even begin to think about operations on polynomials, we need to talk about polynomials. So we need to go back and recall all the different types and parts to a polynomial. So let's start there. Polynomial is made up of terms. You've probably heard this many times, even from myself. Polynomial is made up of terms. A term is any combination of an exponential expression, a real number, or a variable. And we know that exponential expressions can also be real numbers and variables, right? So really it's a combination of exponential expressions. For example, 4x, 9x squared, 5 over 2, z to the 15th, negative y to the third, which is different from parentheses negative y to the third, right? That's definitely different. 1 over z squared, x over y, 10, 400, 13x to the 19th, right? So there's a whole bunch of different things that can be terms. But notice what's common between all of these is that you do not see addition or subtraction. No addition or subtraction, right? It's all multiplication or division. So a term is just multiplication or division. It's the product of any sort of multiplication or division. I'm sorry, any sort of exponential expression. So if you want to say combination, that means product. Very important fact. Because later on, when you throw in addition and subtraction, those make polynomials. We'll talk about that in just a sec. Alrighty, but let's take a look at the pieces of these terms. The pieces of these terms start with a coefficient. A coefficient is a number that sits in front. So when you have something like 4x squared, right, then the coefficient would be the 4. That would be the coefficient. So for the ones we have listed above, 4, 9, 5 over 2, those are all visible coefficients, right? Those are the first three. 1 is also a coefficient. Remember, if there's nothing sitting in front of the variable, it still has a coefficient. It's just an invisible 1. So like here, well, that one's negative 1, but we'll do here. X over y, right? The coefficient would be 1 times that, right? 1 times x over y. And then there's a little bit of debate about the 10. 10 is what we also call a constant. So the constant is anything that doesn't have a variable, right? Remember, we kind of remember that from last time. But technically, there's an invisible variable there of x to the 0. Technically, right? Technically, there's an x to the 0 because 0, not 6. Because anything to the 0 power would be 1, right? We have 10 times 1. So some people believe it is a coefficient, but for the purposes of this class, we're going to say it's not. Okay, so we're going to say 10 is not a coefficient. Later on, you may hear an argument otherwise. But we're just going to say the stuff with visible variables are coefficients. All right, cool. And remember, 10 would be considered a constant. So 10 isn't just left off, he's not unimportant, but he's considered a constant, something that's not going to change when you plug in a variable. A constant. Alright, so like we said before, none of these have addition or subtraction, right? They're all made up of coefficients and variables together to get exponential expressions. Even if they don't have a visible exponent, remember there's an exponent of 1 there, so they are all exponential expressions. When you start putting them together with addition and subtraction, you end up getting what we call a polynomial. So this first one, we've got 9x squared plus 4x minus 10. We took 3 of our terms and we made a polynomial out of it. We'll talk about the names in just a sec, but there's many different types. You don't have to take 3. You can take as many as you want. The examples I've listed here are 3, just for some reason. But you can take as many as you want. We can have binomials. You can have trinomials. That's 3 terms. You could have, 4 polynomial terms, 5 polynomial terms, 6 polynomial terms. I've seen some as big as like 100 polynomial terms. You can even go infinite. There's a way to write an infinite number of terms. But basically the idea is you're just putting terms together with addition and subtraction. Cool. Now there is actually convention to writing these. We tend to write them in what we call descending That's not how you spell descending. Sorry. Get out. There we go. Okay, so descending. Descending exponent order. And then you can kind of put this in parentheses as well. We also tend to like them, or write them, not algebraically, alphabetically. So x's come before y's come before z's, things like that. I put those in parentheses because we probably aren't going to deal a lot with the ones that have multiple variables. If we do, we just know we put them in alphabetical order. But the descending exponent power is very convenient when it comes to things like degrees, which we will talk about a little later, but like, I think, yeah. So they come with degrees, which we will talk about later, but it's just basic convention, right? So you write it in the highest power first, and then you go down. So let's try doing that. Let's name the terms, coefficients, and constants of the following. First, let's put it in order. Excuse me. Okay. So first, let's put it in order. Which one of these would be first? I would say y to the fifth, right? Luckily, none of this has any x's or any other variables, so we can just put them in order from highest power. So we've got 8y to the fifth. Then we've got negative 9y to the fourth. Notice that the negative gets dragged with the 9, right? So it's not, I don't get to choose which ones are negative or positive. The 9 is negative. In other words, I can think about this as 8y to the fifth plus negative 9y to the fourth. Okay. Next comes 3's, so minus 6y to the third. I don't see any squareds, so that's okay. I just go in order of what I have, right? I don't need to add a 0y squared. Sometimes we'll do that, but it's not necessary. So instead, I'll just say plus y, and then plus 12. And that will be my power, my exponents in the right power. All right, they're in the right order. Now let's list those terms, coefficients, and constants. So the terms, label it T. What would a term be here? So what would be the terms here? What were the things that were switching around? Well, one of them would be 8y to the fifth, and then negative 9y to the fourth, negative 6y to the third, y, and 12. Notice it was everything that was separated by a plus, right? So everything that was separated by a plus. And remember, if we think about those negative ones as being plus negative 9, it's whatever's being added, right? So you split them up by terms. Cool. Let's talk about the coefficients. We'll do coefficients, remember, we're going to do everything that sits in front of a variable. So 8, negative 9, negative 6, y's got a 1 in front of it, right? Now we could say 12 maybe, right? We wouldn't be wrong, but we also wouldn't be right. It depends on the person you're talking to. Really, though, those are our 4 coefficients. 8, negative 9, negative 6, and 1. And then last but not least, our constant is the one that does not have a visible variable, right? That constant thing that's being added, that constant thing that wouldn't change if we plugged in for y, that would be our 12. Okay? All right, cool. So we've got our terms, coefficients, and constants. That's the basic breakdown of polynomials. If any of those pieces, coefficients, constants, polynomials, terms, descending powers, right? If any of that was confusing, go ahead and stop the video now, because we're going to go on to combining them using adding, subtracting of polynomials and like terms. And if you don't know what a term is, you're not going to know what a like term is. So make sure you get your questions answered as we go along. If you need to, pause the video. Okay, adding and subtracting polynomials. Like I said before, we need to identify like terms. You can only actually add together things that are alike. It comes out of PEMDAS. So remember that thing, PEMDAS, many years ago? PEMDAS. I actually learned it as PEDMAS. Don't ask me why. They just switched the D and the M for some reason. But it means parentheses, exponents, multiplication, division, addition, and subtraction. It's the order you're supposed to do calculations in, right? It's the order that you're supposed to stick stuff together. So because of PEMDAS, we can't just willy-nilly add everything together, right? Because multiplication or exponents, right? Y to the fifth means y times y times y times y times y. Because that comes first, we can't combine it with y to the fourth, right? So we can't just stick it together and say, you know, I don't even know how you would do that, right? Because addition and subtraction become last, we can only combine things that are alike. That's the reason we have like terms. So let's talk about what exactly is a like term, right? What are the things we can combine? I've got some terms down here, quite a few of them. Let's see if we can find some like terms. Now, like terms have the same variable or variables and the same exponent or exponents in the same order. Okay, so let's see if we can find some things that match up with this first term right here. So we've got 4x. Which one of these other terms would be a like term, meaning it has the same variable and the same exponent on that variable? What do you think? Talk about it. If you need to, do it for about 30 seconds. Okay, I hope you had some time to talk about it. The only one here that would be a like term, well, first off, I can ignore all the things that say y or all of the things that are constants, right? None of that would even come close to matching with an x. It's got to have an x on it. It needs to have the same variable. So my choices are 9x squared, 6x squared, or 9x, and I want the same exponent as 4x. Therefore, the only one that would fall into that category would be 9x. So 9x is my only other like term. So those guys are like terms. Cool. Let's do another one. Do this one together. Let's do 9x squared. Who would match up with that? Well, again, my choices would just be from the x's. I know it's not that one because I just used that one. It's not the same exponent. So I have to have the same exponent and the same variable. So the same variable would be an x. So my choices are 6x squared or x to the sixth. The same as this exponent would be 6x squared. So those two go together. Cool. Let's just keep going down the line here. Now I've got y. So what powers on y here? Well, first off, I want to see what variables I can consider. So I've already used these first three, so I'm down to these last seven. I want anything that says a y. So I don't want to consider this guy. I don't want to consider, well, actually, let's do it this way then. Instead of what we don't want to consider, let's write down what we do consider. Okay, oops. My pen back. Okay, so I can, so this is the guy in question, right? Y. Here's a y. Here's a y. It looks like those are the only ones that are y's, right? So we got y's, and we need the same exponent. Which one of those other ones besides the first guy has the same exponent? That would be 8y, right? So just like 4x, 9x, y, and 8y, they both have an exponent of 1. So those two guys are like terms. Sweet. Alrighty, next up, let's consider y to the 0. I know a couple of you are thinking, this one doesn't have any like terms, Miss K. Ha ha ha, this one's all by himself. He's a loner, whatever. No, he actually does. Remember, this is not the simplest form of y to the 0. What is the simplest form of y to the 0? What is anything to the 0 power, if you remember from last time? Exponents, anything to the 0 power? That equals 1. So he's a constant. He's actually a constant. We always deal with things in the simplest form. Never, ever, ever take for guarantee that something is already in the simplest form. This one definitely wasn't, right? So not only does he match every other constant, he is already a constant himself. So 1 would be a like term, as well as 15. So he's actually got 2 people who are the same as him. So make sure you always simplify first. Alright, so that leaves those guys. And then we have one more, x to the 6th, which unfortunately there isn't anybody left, so he couldn't possibly pair up with anybody. But even if he did, he would have to have an x and a to the 6th. So the only other thing that might pair up with it would be like 9x to the 6th, 18x to the 6th, stuff like that. But he doesn't, and it's not a guarantee that he did, so he's all by himself. He's the loner. Alright, if we take a step back, we can see we have lots of different types of like terms. But any of the different colors I couldn't combine. I couldn't combine anything green with anything pink, right? Or anything blue with anything pink, anything like that, right? Because they are unlike. All right, cool. If you have any questions at all about like terms, make sure you pause the video now so that you can get them answered. Otherwise, we're going to go on and see what like terms have in common so that we can actually combine them. Alrighty. So take a look at this. I've got two like terms here, 4x squared and 6x, right? I've got 4x squared and 6x squared. They both have x's and are squared, right? Now because of that, if I wanted to add them together, right? I could go ahead and do that. And because they have the exact same thing on the end, I can take that thing out. So this is distribution property, remember? So if I had something like this, I could distribute the x in, and then I would get back to where I started. In other words, here I'm taking it out. Because that part is in common, I can take it out. And when I do that, I end up with this second statement here. 4 plus 6, all of it times x squared, right? So that's, think distribution property. Then I can go ahead and combine some things together that actually combine. 4 plus 6 is 10. And I end up with 10x squared. Now, that's the reason it works. Obviously, if you want to take the jump and just add the coefficients, that's fine. But this is what's happening. The distribution property is what's happening. This is the reason they have to be alike. If this was x squared and x cubed, well, I couldn't pull out the x squared like I just did, right? If they didn't match, then I couldn't combine their coefficients. But if they match, I can take out the x squared and can combine their coefficients. Remember, coefficient means the number in front. So that's why they have to be like terms. That's sort of a sidestep to the issue with PEMDAS. We use the distribution property, or the distributive property. All right, cool. So let's try that out on a few down here. Example 2.2. Add these two polynomials by combining like terms. So let's do this first one together. I'll let you guys handle the second one alone. Let's take a look at this. So I've got this first, what we call a binomial. Bi means two, so two terms, like a bicycle, right? So I've got 4x squared plus 3 plus the second polynomial, the second binomial, 5x squared plus 9, right? So I've got these two polynomials I want to add together. Luckily, though, just like when we were multiplying monomials, multiplying terms together, everything is commutative. Addition's commutative. So I can add these in any order I want. So I can add 4x squared plus 5x squared plus 3 plus 9. Essentially what I just did was rearrange it by like term, right? So I looked at these two things. I said, okay, these two guys both have an x squared on them, so they must be alike. And these two guys are both constants, so they must be alike, right? So I put those two together, and I put those two together. Now I can simplify that a little bit. I can use that distribution thinking, and I can say, okay, 4x squared plus 5x squared, I have 9x squareds. And then add the constants, plus 12. And I'm done. I can't combine those last two because one of them is an x squared and one of them is a constant, right? So the most I'm going to get out of this is another binomial, 9x squared plus 12. Alrighty. Take this time now to pause the video, start working on this second problem. If you have any questions, you can call the sub over and get them answered at the same time. But I'm going to give you about 30, you should just pause the video for about however long you need to so that you can simplify the second problem using combined like terms. Alright, so I hope you had some time to try this one out on your own. I'm going to, so again, it's the same idea that because they're all being added, right? Technically this last part over here is still being added -6. But because they're all being added, then I can combine them using commutative property. So I can just go ahead and combine like terms. So I'm going to combine these two guys because they are alike, right? X squareds, I get 9x squared. The x's I can combine. I have to be careful. 7x plus -6x is going to be the same thing as 7 minus 6x, right? So plus 1x. And then the constants, I have Can't honestly for the life of me tell whether that was a positive or negative 9. You guys probably can, but hold on. It was a negative 9. Okay, so then in the constants, we have negative 9 plus negative 2 is negative 11. So you should have also gotten 9x squared plus x minus 11. When we have three terms like this, it's called a trinomial. So you should have gotten the trinomial 9x squared plus x minus 11. Fabuloso. Alright, next thing we're talking about subtracting polynomials. Luckily, it's almost exactly the same. We just have one additional step. Because instead of adding, right, adding is super commutative. You can move it around every single way you want. 2 plus 3 is the same thing as 3 plus 2. But we have to remember, 2 minus 3 does not equal 3 minus 2, right? So because of that, we have to kind of manipulate a little bit, just a little bit, so that instead of a subtraction problem, we have an addition problem. Addition is much easier. We don't need to write that down. So addition is what we're aiming for. Aiming to change it into an addition problem so that we don't have to deal with subtraction. So in order to do that, what I'm going to do is I'm going to distribute this negative in the second problem. So in this problem here, I have 7xn squared plus 5 as a binomial, minus this entire second binomial, 6n squared minus 6. And if I think about this piece by piece, I'm not just subtracting the n squared part, I'm also subtracting the constants. So I want to make sure I account for that. Now people always say, well, can't you just remember it's subtraction and subtract them together? Yes, you can. You can remember it's 7n squared minus 6n and 5 minus negative 6. But 9 times out of 10 people don't do that. They don't remember, right? They think of the addition and how easy it was and they just move on. So instead, just take another millisecond step, distribute the negative so that instead, this first guy, you didn't do anything to him. Whoa. Sorry, guys. Okay. So we're going to distribute first. This first binomial, he's unaffected, right? He doesn't have any negatives in front. He's just going to stay there. But the second guy, I'm going to multiply everything by negative 1, because that's what it says, right? Or subtract everything, which means distribute. I get negative 6n squared. Negative times a negative is going to be a positive 6. So I've basically flipped the sign on everything in the second binomial. Now it's just an addition problem. I know it says, plus minus there, but technically that's the same thing, right? So we now just have addition, and we can do the same thing we did in the last one. So combining some like terms, we've got these two, the n squareds. 7n squared plus negative 6n squared is going to be n squared. And then we've got the constants. Oops. 5 and positive 6 plus 11. So that will be our final binomial. Now, if I hadn't done that distribution part, I might think it's 5 minus 6, right? So 5 plus negative 6. If it was 5 plus negative 6, I would have negative 1, and I would have the wrong constant, which might send my rocket ship the wrong way, or whatever's happening with this equation or expression, because negative 1 is definitely not the same thing as 11. All right, cool. So try out this second problem. Same kind of dealio. You've got a subtraction here that you need to take care of first. Once you do that, you can use your combined like terms. You should be able to get down to another trinomial. Try it out. Get your questions answered at the same time if you have. Okay, so I hope you had some time to try it out yourself. If you didn't pause the video, please make sure you do so. First, I'm going to start with distributing, right? So distribute that guy into everything. Notice there are 3 terms being subtracted, 3 terms get switched. So the first one stays the same. Negative 6m squared plus 5m minus 9. And then I'm going to subtract 4m squared minus 3m. And the last one was already negative, so he switches back to a 10. Now I combine some like terms. These two are alike. Those two are alike. So negative 6m squared minus 4m squared would be negative 10m squared. 5 and 3 are alike. Or sorry, m and m are alike, not 5 and 3. But 5 minus 3m would be negative, no, it would be positive 2m. And then last but not least, I have negative 9 and the constant positive 10, so plus 1. And that is the trinomial you should have gotten when you subtracted them. Okay, that is addition and subtraction. Addition and subtraction, polynomials come straight out of like terms. We are going to move on to multiplication, which involves a lot of our product rules. So if you have any questions right now, please make sure you get them answered before we move on. All right, multiplying terms, multiplying polynomials and multiplying terms. Let's start with just terms together. Luckily, this part's just a review. We've done something like this, right? So we had a problem like this last time. We were discussing product rule. So we're going to use product rule again to multiply these two guys together. Okay, so I have two what we call monomials. It means one term, right? One term. I've got 3x to the fourth times 5x to the third. 3x to the fourth times 5x to the third here. And we're going to do this one here. Remember, when you have stuff like this, you can see it instead as 3 times x to the fourth times 5 times x to the third, right? So all of those pieces broken up. I've got times, 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 times. Because I've got multiplication, 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 I can rewrite it so that the numbers are in front. I've got the 3 and the 5, right? And then the variables are at the end. The x to the fourth and the x to the third. Oops, that x to the third was from the second term. So I've split up the term into its coefficients and its variables. You see what I've done there? And then I can combine them individually. 3 times 5 is 15. And then we use product rule, right? 2 of the same base, add the exponents, x to the 7th. And we get 15x to the 7th. So the multiplication of 3x to the 4th times x to the 5x to the 3rd, the coefficients become 15, you add the variables to get x to the 7th. And we still end up with a monomial. Awesome, awesome. Let's try that out with something like this. So let's try the same thing. I've got this first term here, right? So this first term, negative 4a cubed. Got this second term here, 3a to the 5th. Sweet. I'm going to rewrite this so that my numbers, I'm going to split it up by number and by coefficient, I should say, because we know that technical term now. So by coefficient and by variable. So the coefficients will go over here. The variables will go over here. Coefficient over here, variable over there. And then everything's still being multiplied. The reason I can do that is because everything is being multiplied. Notice I'm not adding these terms here, right? If I was adding them, they would be unalike, and I could actually not add them, right? Because I've got 3 to the 5th and I've got a to the 3rd and a to the 5th, right? And those are definitely not the same exponent, but I'm not adding, so it doesn't matter. All right, now I'll go ahead and combine. I get negative 12, and over here I'll use the product rule. 3 plus 5 is 8. So I gotta pay special attention to whether I'm adding and I can use like terms, or whether I'm multiplying and I use product rule. Okay, and it's an easy way to remember because product means multiplication. So if I'm multiplying, I use product rule, right? Multiply product. Addition, like terms. Addition, like terms. Okay, cool. And now we're down to one monomial of negative 12 a to the 8th. Cool. In this last example of two terms being multiplied here, we have multiple variables, but that doesn't matter. Remember, notice everything here is still being multiplied, right? It's all still being multiplied. So I'm going to let you guys try this out. Use that commutative property, that switch around rule, and try and see if you can come up with what happens, or what do you get when you simplify 2m squared z to the 4th times 8m cubed z squared. So pause the video now and give it a shot. Alright, I hope you had some time to try it out. Hope you paused, got questions answered, right? Because remember, I've been saying that all day. I'm going to keep saying it. If you have questions, answer them. Get them answered, right? Do not leave today with questions. Otherwise, you will be horribly confused for homework. Alright, so I'm going to rearrange this. I've got this first term here and this second term here. I'll split it up by number. So 2, and then I'll put the m's together, and I'll put the z's together, right? Remember, I want to split it up by things I can actually use product rule on. I can't combine m squared and z to the fourth, right? Because those are not the same base. They must have the same base. So it's kind of a like term situation, but not really the same, right? Because it doesn't need to be the same exponent, it just has to have the same base. And then I'll put 8 over here, the coefficient there. M cubed groups up with the other m, and z squared groups up with the other z, right? So I split it up by type. Since everything's still being multiplied, I can do that. And when I combine them together, I get 2 times 8, which is 16. Product rule here says I have 2 m's and 3 m's, that makes 5 m's. And product rule over here says I have 4 z's and 2 z's, that makes 6 z's. So I end up getting 16m to the 5th, z to the 6th as my final monomial, my final term. Awesome. Alrighty. Please, 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 make sure you know what you're doing here. You need to know what you're doing here because when you multiply any other size polynomial, it comes back to this. If you can do this, you can multiply any polynomial you want to. Absolutely anything. So let's try it out with bigger polynomials. Now, there's only one other thing. Actually, let's just dive in. So find each product. Example 4.1, find each product. This one, you probably know what to do. I would hope you know what to do. Hopefully 3 of you, at least half of you are sitting there going, oh my gosh, I can do this. You just distribute, right? Hopefully the word distribution just popped into your head. Or if it didn't, you at least saw like the little rainbow thing. That should be review. If it's not, that's okay. We'll learn it right now. So when you have something on the outside like this is just a number. And I'm going to get rid of that because now you can't see that number. So when you have something on the outside like this, just a number, you just have to distribute it in, just like we did with the negative, right? So we're just going to distribute this negative 2 in. When we do that, we get this number times 8x cubed. Now the only thing that we can combine are the actual numbers. So we end up with negative 16x cubed. Same thing on the other side. Negative 2 times negative 9x squared, right? So this is the second one. Multiply it this way now. Now, again, the only thing I can combine are those numbers. So I get a positive 18x squared. And that's how you multiply in a simple number, right, to a binomial. Works with a binomial, trinomial, anything bigger. You can do as many terms as you want. If you're only multiplying one thing in, you just have to use distribution property. Just distribute it to everything. Same thing goes for monomials. Okay, so same thing goes for if you're multiplying by something with a variable, right? Remember I said before, variables really think they're cool. They're really not that cool, right? They're really just numbers we don't know yet. They have to follow every single same rule, right? So if you can multiply a negative 2 in, you can multiply a 4c cubed in. That's all you need to know. You can multiply a 4c cubed in. Cool. So let's try that out. Multiply that guy in. End up getting 4c cubed times 5c squared plus 4c cubed times 3. I just wrote it out so that you could see that I'm multiplying each one by 4c cubed. So I've got this one and this one. And now this might take like another additional second of thought because I'm actually multiplying c's this time, but then it just starts to look like one of the problems up here, right? So I said before, as long as you've got this step down, you've got this step down. All right, so I can multiply the numbers together. I get 20. Oops, don't want to use green though. Use red. 20. And then I have 3 c's and 2 c's. That gives me c to the 5th. Plus, I don't have any more c's on this second term, so it's just the numbers 12c squared, or cubed, pardon me. And there is my final binomial. Cool. In other words, I gave each term an additional 4c cubed, right? I distributed in the monomial. This last one I'm going to let you guys try. It looks a little bigger, not that big a deal, but it's the same format as this one, right? You just use the distribution property and then multiply monomials. Use the distribution property, multiply monomials. So try it out now. If you have any questions, remember, get them answered, and I'll be back in about, some time, 30 seconds. Alright, so I hope you had some time to try this one. When you distribute them in, I'm not going to take, well, yeah, I'll take time. So here I've got 5x squared times negative 4x squared. Do it again to the second one, right? I've got plus 5x squared times 3x. And then the last one, I've got, let's see, 5, so plus 5x squared times negative 2. So I've got kind of three little zones going on here. Now I can simplify that. I'm going to write it all in pink. I guess kind of like that, so you can see what we're doing. Alright, so then I'm going to simplify that. 5x squared times negative 4x squared. Well, the 5 times the negative 4 is going to give me negative 20. And then 2 x's and 2 x's makes 4 x's. Plus, over here, the green stuff, I've got 5x squared times 3x. Well, the 5 and the 3 are going to give me a 15. And then the 2 x's and the 1x give me x cubed. The very last one, I don't have any more x's to multiply, so it's just going to be x squared, but 5 times negative 2 is going to be a minus 10, and then the x squared. And that binomial, or sorry, pardon me, trinomial, right, for 3, triangle, it's my final answer. Alright, hopefully you got the same thing. Just using distribution property, right? Distributed in multiplying monomials. Okay. The next thing we're going to talk about is multiplying slightly bigger things. But here's the thing. It is all the same as what we just did. It is exactly the same. It is not different. It's just distribution property over and over and over again. Now, there are many, many different ways to organize this. Some people use a method called FOIL. Some people use boxes. Some people use tables or vertical method. There are many different ways that you might see over the next few years. Even you maybe have seen before. And if you have one of those, use it. Totally fine. If you know what I'm talking about and you know how to do this and you love FOIL to death, go for it. But honestly, it's all the same as distribution property. Okay, so there's just distribution property. Okay, so however you want to organize it, totally fine. There's just a few things to keep track of. So over the years, teachers try to give you many different options to be able to organize your thoughts. That's all these methods come down to. Okay, it's thought organization. But what it comes down to is if you have something like this, a trinomial times a binomial, it's exactly the same as a monomial. All you have to do is think about the first one as 3 separate monomials. So think of it as 3 separate monomials. And then distribute each one to the second binomial. That works for any combination, whether you're talking about binomial to binomials, trinomials, trinomials times 4 terms, right? You're just going to do distribution a whole bunch of times. So this first one, I'm going to think of this first case as the red problem. I'm going to multiply a 6x squared times the 3x squared plus 2. When I do that, I end up with 18x to the 4th plus 12x squared. Okay, it's the exact same problem we just did as up here with the 4c to the cubed, right? Same thing here. I'm going to consider this second green term as its own monomial, and I'm going to multiply that in. And then I get this guy. Okay, the last one, I'm going to multiply the 4. Oops, sorry, didn't mean to do that. Not on the problem. Meant to go down here. So I'm going to think of the 4 as its own term, right? Its own monomial. I'm going to multiply that in, and I end up getting this. Then I just look at all 3 together. Okay, so it's like I'm doing three versions of problem B so that I get every single combination, right? So at the end of the day, if I have 3 terms and 2 terms, I should get 6 pairs, 6 combinations, right? So I got 1, 2, 3, 4, 5, 6. I know that everybody got multiplied together. That's all it is. After that, it's just one big, huge addition problem, and you combine like terms. So I happen to have, let's see, I happen to have a 12x squared, so I combine those to 24x squared, and it looks like everything else was actually a single term. So I ended up with a 5-term polynomial as my answer. Yeah, it's big, whatever, right? It's just 3 separate problems. I'm just dealing with 2 at a time. I'm not trying to do all 5 at a time. I'm not trying to do all 6 at a time, right? I take one term, I multiply it. I take the next term, I multiply it. So it's not anything new. You're not learning new skills when you multiply the bigger ones. The bigger ones are just big. Big things just are big. That's all. That's really all they are. So let's try that out here. Let's try that out here with this binomial times this binomial. I have the binomial 5a minus 2b times the binomial 3a plus b, right? Yeah, I've got multiple variables. I could care less, right? Because I'm not dealing with this variable by variable. I'm dealing with it term by term, right? So I'm going to split this up and take my first binomial, and that's the one I'm going to split up. Always split up the first one, right? You're welcome to switch them and then split up the second one. That's fine too. But always split up one of them into the other one. Don't split up both, right? Eventually we will, but it's, yeah, anyways. I split up one of them. So I'm going to take 5a and negative 2b, and I'm going to treat them both like separate terms. I'm not going to treat them like a binomial together, right? Treat them like separate terms. And I'm going to multiply each one of those times 3a plus b. Times 3a plus b. So now I've made myself sort of too many problems, right? Too many problems. I will now multiply each one into too many problems. So eventually we did split it up again. So really it didn't matter, but we're splitting them up once and then twice. So now I will do this one. That would give me 5, let's move my little box over, 5a times 3a plus, then we'll do the second one. I'm not even looking at the second half of the page right now. I don't even care. I'm treating this as one monomial times binomial, right? And then I've got 5a times b. Cool. Finish that guy up. 5a times 3a. 5 times a is 15. And a times a would be a squared. Cool. The second one, unfortunately, I have a 5, an a, and a b. None of that is the same base, so I can't combine anything. None of those are numbers. So it just says a 5ab, which is fine, right? Whatever. Okay, cool. If this was the only problem, if it was just 5a times 3ab, I'd be done. I have my two terms. Cool. Let's go do the exact same thing over here. And notice my little box isn't even looking at the first half anymore. So now I just multiply this guy, and then, oh, sorry, I'll use a different color. That guy. Alrighty. So what I have now is negative 2b times 3a. That's another one. And then my other one would be negative 2b times b. Okie. Again, I'm not looking at the red and the blue. I don't care about the red and the blue right now. I'm just focusing on this second problem like I did with the other ones. My first one, well, I have a and b. Those guys aren't going to combine, so it's just ab. Notice we wrote them in alphabetical order, right? So remember, commutative property means you can switch anything you want. Always want to write it in alphabetical order, and you'll see why in just a sec. But if I multiply negative 2 times negative 3, I get negative 6. And then the last term, negative 2 is all by itself, so no numbers to combine, but I have two b's. B times b is b squared. Awesome. Now if you look, I started off with 1, 2, 3, 4 terms, right? Or sorry, I have 2 terms and 2 terms. Multiply each of them together, I should get 4 terms, right? 2 times 2, and it looks like I did. 1, 2, 3, 4 colors. Sweet, everybody got paired up. Now the last step, it's an addition problem. I'll just look for some like terms. That's the reason we wanted to write them in alphabetical order, so that I could see these two middle terms are in fact the same. So I end up with, we'll write it over here. We'll just bleed into the next problem. 15a squared. Let's see, positive 5 and negative 6 gives me a negative 1ab minus 2b squared. That is my final answer. Alright, so just split them up. That's really all it is. Split it up and then combine like terms. Okay. Now my stylus is a little big, so you'll probably have a little more room for this next problem. Go ahead and try that one out. See how it works. Remember, you've got a monomial times a trinomial here, but we've already, or sorry, a trinomial times a binomial here, but we've already seen that it's really just, you should end up with 6 terms, and you should end up being able to combine some stuff. That's really all it is. So go ahead and multiply it out. Alrighty, I hope you've had some time to pause the problem. I'm going to try and be real squishy about this, so I'm going to kind of block off our last problem here. I've got a binomial, or trinomial times a binomial. So I'm going to go ahead and split up this binomial into this trinomial into three separate monomials, right? I'm splitting it up into three terms. So I'll start with one at a time. So the 3m cubed times the 3m plus, minus 5. Minus 5. And then I got the orange one. Minus 2m squared, 3m minus 5. And then the last one. Plus 4 times 3m minus 5. Alright, I'm going to finish the entire blue part of the problem. So I'm doing this monomial one like it's the only thing. Okay? So I've got 3m cubed times 3m ends up giving me 9m to the 4th. Right? So just that first monomial, that first term times the first term. First term times the second term gives me a negative 15m cubed. Sweet. Now I'll do the pink one. Negative, I gotta watch out for that negative. I drag the negative down. Negative 2m squared times 3m is going to be a negative 6. I have m squared and m gives me m cubed. On the outside, I've got a negative 2m squared times a negative 5. Negative times a negative is a positive 10. 2 times 5 is 10. I have no m's to combine, so m squared. Very last one, do the green one. 4 times 3m would be 12m. 4 times negative 5 would be negative 20. And I should end up with 6 terms, right? I've got 3 times 2, and I end up with 1, 2, 3, 4, 5, 6. There we go. I found them all. Fabulous. Now I'll just do some like terms, combining like terms. Let's see. I'm going to ignore colors now because it's all one big string, right? So I'm not looking at colors anymore. I've put them back together, right? I've put them back together. I don't have any other fourths. So I've got 9m to the 4th. I've got a few cubes, so minus 21m cubed. I don't have any other squareds, no other singles, and no other constants. So it looks like that is my final answer. 9m to the 4th minus 21m cubed plus 10m squared plus 12m minus 20 is the combination of these two. Notice we ended up with a very large answer, but because we broke it down into 3 separate pieces, we didn't have to worry about that, right? We didn't have to worry about it being a large answer. We just had to make sure we keep track of everything. That's all it comes down to. Okay, we're going to skip D. I don't do this often, but we are going to skip D just because I want room to handle this type of problem. So I'm going to kind of clean it up a little bit. You don't have to erase anything. Please don't erase anything. I'm just doing it because my stylus is large. That's all. Alright, so C. C says we have 3 different things being multiplied. 2 times x squared times a binomial, 2x squared times a binomial of x plus 1 times a binomial of x minus 3. Now, just like when we were multiplying terms, everything here is being multiplied, right? So we can use any combination we want, associative property. I can multiply either one or any 2 that I want to first, then multiply the last one. What I don't want to do, what I do not want to do, is distribute, okay? That's not what I want to do. Do not do that. The reason is, that's not what it's telling me to do. There is no giant parentheses around those 2 second terms, right? If there was a giant parentheses around this, then yes, I could distribute, but I'm not, right? I'm not doing that because there is no ginormous parentheses around this. So instead, I'll just pick my 2 favorite and I'll multiply those. I think I'm going to start with the first 2 because, you know, why not? So this would be 2x squared times x plus 1. Well, that's just already a monomial times a binomial. We've done that so many times today. So I'll multiply the 2x squared times the x. That's 2x squared and another x gives me 2x cubed. Multiply out that times 1 is just itself. And that's what I end up with for my first half. Cool. Now that is going to be multiplied by the other one, x minus 3. That's going to be multiplied by the other one. And let's go ahead and do that. So I'll multiply this first term by the binomial. I get, I guess we'll go over here, 2x cubed times x minus 3. And then the second one, we will make red. This term times that binomial, plus 2x squared times x minus 3. And now we can just simplify another monomial times a binomial, monomial times a binomial, monomial times a binomial, right? So this would, the blue stuff, let's see, 2x cubed times x, that's just another x, so 2x to the 4th, 2x cubed times negative 3, x's, no more x's to multiply, but I get a negative 6. Now I'll do the red one. Very, very similar, right? 2x squared times x is going to be a positive 2x to the 3rd. Last one's going to be a negative 6x squared. Cool, and I should have, let's see, that was a binomial times a binomial. That's 2 times 2. I should have 4. 1, 2, 3, 4. Good, I got everybody's combination. Now I can combine some like terms here in the middle. No more fourths, so I get 2x to the 4th. Some here, I got some negative 6, and positive 2 is negative 4x cubed minus 6x squared. That's my final answer. Alrighty, so this problem, yes, it had 3 things to do. That doesn't mean you have a whole nother process, right? You just break it down into little bits. That's usually how math works out. Break it down into bits at a time, use your toolbox, and get through the problem to the most simplest form. Sweet. Okay, let's do these problems down here. So again, we crossed out D because we just didn't have room, and it's, you know, exactly the same as this one. So let's just skip to E. I'm going to let you guys try this, and I want you to see what happens. You try this problem out. Binomial times a binomial. You know how to do this. In fact, it's a very simple binomial because most of these coefficients are 1. So multiply this out and tell me what you get. We'll be right back in a couple seconds. Okay, so maybe it's the time to try this. I hope you broke it down piece by piece. Got P times this whole thing, so P times P minus 7. The other one, 7. So plus 7 times P minus 7. Now, some of you I know definitely can do this in your head, and that's fine. You can break it down. You don't need to write it out like this. But for those of you who this is the first time you're ever seeing it, you've never done this before, you definitely want to write it out like this to make sure you get all the combinations, right? All right. Pink one ends up being P times P is P squared. That goes negative 7P. The blue one, 7 times P is positive 7P. Minus 7. Oops, not minus 7. Silly Miss K. 7 times 7 is not 7. It's not even negative. So yeah, it is. 7 times negative 7. No, negative 7 times. No. 7 times negative 7 would be negative 49. Alright, and then we combine like terms, and check out what happens in the middle here. We have a negative 7p plus 7p. These two end up canceling each other out. We end up with p squared minus 49. So sometimes that happens. Sometimes the middle term cancels each other out. We'll see way later on at the end of the year going backwards. It's called difference of squares. It's a pretty powerful little thing. However, right now, just notice that it happened regardless of whether you knew it was going to happen or not. Okay? So this just happens from time to time. I'm just showing you that sometimes this happens. And it happens when you have something like this. They look almost identical, right? You've got the same monomial in the front, the same variable in the front, you have the same number at the end, but the only thing that's different is the signs. That's how this ends up happening. Oops, that's how this part ends up happening. And you end up getting just p squared minus 49. Let's try it again. Now, what this kind of pattern says I should get, what I should get, right, is the square and the square. So it should be 36x squared minus 16. It should be 6x squared and 4x squared, 4 squared. But again, I don't need to know that. In fact, I don't want to take that for granted. Instead, I'm just going to do what we've been doing the entire time. So I'm going to multiply the 6x to the second binomial. So 6x times 6x minus 4 plus 4 times 6x minus 4. I just broke it up into monomials. Distribution property, distribution property. All right, first one, I end up with 36x squared minus 24x, right? So 36, 6 times 6, x squared. And then the second one, 6 times negative 4 gives me negative 24, and then there's no x's to combine. The pink one, 4 times 6x, positive 24x. 4 times negative 4, negative 16. And it looks like I end up getting minus 24 plus 24. They cancel, and I do end up getting what I was supposed to. 36x squared minus 16. All right. So that can happen as well, right? So it just happens when you have the same things but different operations, right? So 6x squared plus 4, 6x squared minus 4, or p plus 7, p minus 7. And it doesn't have to be the plus first, right? Because it's commutative, I can just switch it around. But that happens from, case-by-case basis. All right, one other thing we're going to talk about today. When you see something like this, the square of a polynomial. The only reason I'm bringing this up is because people make a faulty assumption about this. They assume it is special, and then they assume they can save time. Nothing here is special. There are no special things in math. Sorry, math is not special. Math is a system of rules. A rule here says this is not special. So when you have the square of a polynomial, it looks like this, or it looks like this. So you have n plus 7 squared. What does not happen is distribution rule. So recall from last time, we have distribution rule. Okay, very similar sounding distribution property, but distribution rule said if you had something like 3m, all of it to the 5th, then you would have 3 to the 5th, m to the 5th. That is still very true. Okay, that is still very true. But notice what's sitting in between the 3 and the m. Multiplication. Multiplication. You can do it with multiplication, you can do it with division. Okay, you cannot use distribution rule on addition. Not on addition or subtraction. Okay, this is where it's different from terms and polynomials. Polynomials use the distribution property. Okay, so spread it out like we've been doing all day. But you cannot do this. In fact, I see so many people doing this, I feel bad because one of my teachers when I was a kid told me this is when God kills kittens. If you do this, God kills a kitten. So please don't kill kittens in my class. I would really like you not to. Do not take the 2 and distribute it out. Okay, that kills people. Don't kill people. Don't kill kittens. Instead, let's just think about what this means. What does a square mean? What does it mean to be a square? Well, x squared, right, means x times itself twice. X cubed means x times itself 3 times. 6 squared is 6 times 6, right? And so x plus y squared is x plus y times itself twice. Okay, that's all it means. Take something and times it by itself. It does not mean distribute, take something by itself. Once you have this, you have exactly what we had up there, except they happen to be the same thing, right? So once you have it spread out like that, something times itself, it's nothing new. All right, so let's give that a try with something down here. M plus 7 squared. I do not want to write m squared plus 49. This does not equal m squared plus 49, okay? Does not equal. Okay? You cannot just distribute it in. Instead, I'm going to rewrite this as m plus 7 times m plus 7. M plus 7 times itself. Okay? And then I'll break this apart. So I've got this first binomial of m multiplied by this side. So m times m plus 7. And then I've also got this second part, 7 times this guy. 7m, parentheses. 7 times m plus 7, right? So I've broken it up just like we did before, just like if they were different, right? Just like if they were different. Just breaking it up. M times m, go with red, m squared, m times 7, 7m. Over here, 7 times m plus 7m. Notice it's positive, right? It's not negative. They're not going to cancel. And 7 times 7 is positive 49. I have a binomial times a binomial. That means 2 times 2. I should end up with 4 things. I do end up with 4 things. Good. That means I got everybody. And then I combine like terms. And just like I said before, notice one of them's not negative. They're not going to cancel. So I end up getting m squared plus 14m plus 49. And notice, this is very different from this because it's got that whole 14m in there, right? You're missing $14, people tend to get upset, right? If you're missing $14 from the budget or $14 from soccer practice, people get annoyed. So don't skip out on that middle term, right? That middle term is what gets missed out if you just distribute the exponent, okay? So don't do that. Alrighty. Go ahead and try this one out yourself. Try it out. See what happens. Alright, I hope you paused the video, had some time to try it out. I'm going to go a little bit faster. So I'm not going to say it's p squared minus 5, or minus 25, right? Instead, it's p minus 5 times p minus 5. Alright, multiply the first guy, so p times p minus 5 plus negative 5 times p minus 5. I wrote it that way because I felt like it. I get p squared minus 5p minus 5p plus 25. And you end up with p squared minus 10p plus 25. Righty. Hopefully you got something similar. I just did the exact same thing we did in the other problem. Okay. Alrighty. We're only going to do one of these last ones because I noticed this video is getting kind of long and you'll probably be pressed for time in class. So we're going to cross off D and we're just going to do C just to prove to you it works no matter what it looks like. So far we've only seen those nice teeny little ones, but remember, the teeny little ones are just the easiest to show you in class, right? Just because they're bigger, just because they have multiple variables, just because they have multiple numbers doesn't mean they're any different. Just because they're bigger doesn't mean you can distribute. In this case as well, we're just going to put 2p plus 3v times itself. Okay, oops, 3v, not 2v. Okay, plus 3v. It is not going to be 4p squared plus 9v squared. Okay? Instead, we're going to split it up, monomial times the second guy. So 2p times 2p plus 3v. And then 3v times the monomial, so plus 3v. Whoops. Don't want to do it that way. I just didn't want to put that parenthesis there. That's all. So 3v times 2p plus 3v. These can get a little, I don't want to say tricky, because they're not tricky. Nothing else happens, right? But these can get a little difficult to see, because there's a lot of 2p, 3v rolling around here. So that's why people make mistakes too, is because there's a lot of the same stuff happening. But just go step by step. Single monomial times single binomial, right? And then just multiply monomial times monomial, binomial times binomial. If you like colors, feel free to break out the colored pencils. I'll be totally fine with that. So I end up getting 4p squared, 6pv, and remember you put it in alphabetical order so that you can see like terms later. Here, we'll do this one in blue. I've got 6pv and 9v squared. Combines, so I've got monomial, or binomial times binomial, should get 4, did get 4, got some terms in the middle that are the same. If I wrote this first one as 6pv and the second one as 6vp, I might not think they're the same, so that's why I want to use alphabetical order. So make sure you always use alphabetical order. And I end up with 4p squared plus 12pv plus 9v squared, right? So it's similar to what I would have gotten had I made the mistake that God kills kittens on, but instead, I end up with this whole 12 term in the middle, and sometimes those numbers get really big. In fact, if you take things to the third power, you miss out on 2 terms in the middle. Take things to the fourth power, you miss out on 3 terms in the middle, and that's when rockets start crashing and bad stuff happens. So make sure you don't distribute, okay? Do not distribute. Distribution rule only applies for those that are being multiplied or divided, okay? Distribution property is what you want to use here. You want to use spread out. Spread it out as much as you can. Alrighty. This has been a long video, but let's do a quick recap of what we talked about today. We talked about what exactly a polynomial is. We talked about adding them, subtracting them, and multiplying them. And remember, multiplying, you can use any form you want. I don't know why it's not going up. You can use any form you want, any organizational method. If you know FOIL, that's fine. You can go for it. But really, at the end of the day, it's just distribution over and over and over again. Okay, cool. Some vocab thing we learned. Terms, constants, coefficients. Gonna need to know those, right? We talked about monomials and binomials and trinomials. If you should probably know those. It's easier if you do remember those. And we definitely talked about square of a polynomial. Squaring a polynomial is just multiplying it again. Okay, it's not anything different. Do not use distribution rule. Alrighty, you have some homework tonight. I believe it's a worksheet, and you should consult Canvas for which ones to do on those. Otherwise, get your questions answered and use this time for homework.